Hi kiddos, this is from Module 2.5, Creating and Solving Compound Inequalities. So our essential question is how can you solve a compound inequality and graph the solution set? So the answer's already here. First, write the compound inequality as two simple inequalities. All right, so that means we have two things going on. It could either be a and or a or statement type of inequality. Now we solve for each simple inequality to find the solution set. Okay, and we'll talk about what that is. And then we can graph each solution and is an intersection of the solutions. Okay, and we'll see an example of that. And or is the union of the solutions. So intersections, if you were to graph them, they look a lot like here's a number line. Okay, an intersection could look something like this. All right, like that. Now an or a union could look something like this on a number line. So here's your number line. All right, and an or statement. So again, this was an and. An or statement would be like saying something like, oh, greater than this number, okay, but definitely less than this number. And I should say or less than that number. Okay, so that's an example of what they're talking about, and we'll see some more as we go through. All right, so let's go ahead and get to a compound statement, which is formed by combining two or more simple statements. So a compound statement can be true or false. All right, so T or F. A compound statement involving and is true when both statements are true. So and has to be both true. A compound statement involving or is true when either one of the statements is true or both. It's possible that both could be true in an or statement. It's possible. So let's see. A dog is a mammal. Is that true? A dog is a mammal. That's true. Red is a color. That's true. True and true. So P and Q, are both of them true? Yes. Therefore, is P and Q true? Yes. Okay. A dog is a mammal. That's true. Red is not a color. Oh, that's false. Now, is P and Q true? No, it's not, because one of the statements is false. So, a dog is a fish. Um, wow, that's false unless there's a dog head fish, which I think there is, but it's not really a dog. It looks like one, but it's not. Red is a color. That's true. Now, is P and Q true? No, because dog is not a fish. Therefore, P isn't true. Therefore, P and Q is not true. Okay, so dog is a fish. That's false. Red is not a color. That's definitely false. So P and Q is true? No, they're both false. Okay, so now P and Q is true when both are true. Okay. Now, P or Q. So let's see. 1 is an odd number. That's true. 2 is an even number. That is also true. P or Q. Yeah, that's true. Both of them are true. Okay. 1 is an odd number. True. 2 is an odd number. Oh, that's false. P or Q. Well, one of them was true, right? So because one of them was true, it's true for the P or statement. Okay, so P or Q. 1 is an even number. That's false. 2 is an even number. That's true. P or Q is true. Yes, because at least one of the statements was true. Now, 1 is an even number. That's false. 2 is an odd number. That is also false. P or Q? Nope. Both of them are false. Therefore, no. Now, P or Q is true when either or both are true. Okay. So that's an example of a compound statement for the and or statements. So solving compound inequalities involving the word and. So combining two or more simple inequalities forms a compound inequality. So that means 2 or more. Okay, so that's 2 or more statements. Okay, so compound inequality and is an intersection or an overlapping region for a simple inequality graph. So words, so compound inequalities of and all real numbers greater than 2, okay, and less than 6. So greater than 2, right? Some number greater than 2 and less than 6. So here's 2. It said greater, so it shades this way. Um, and x is less than 6, so here's 6. Notice how it's hollow because it can't be 6. 6 isn't belonging to it, but less than goes this way. So notice for this statement, this area all in here would be true. Is 4 greater than 2? Yeah. Is it less than 6? Yeah. Is 5 less than 6 and greater than 2? Yeah. Is 3 greater than 2 or less than 6? Yeah. So anything in this region would be true. Anything outside, like is 1 greater than 2? No, that's false. But it's less than 6, well, it doesn't matter. It's an and statement. It's got to be true for both. So anything on the outside is really just false. Same thing with 0 here. Okay, and 2, 2 itself, that's false, right? 2 is not greater than, 2. That doesn't make sense. Is 6 less than 6? No, it is 6. So those are false. Okay, so all numbers greater than 2 or equal to 2. So x is greater or equal to 2. Notice how the shading is filled, right? Because it's the equal symbol right here, greater or equal, all right, than 2. So that would be true this time. 3, 4, and 5 are still true because they're within that area. Um, Shaded region for 6 because again 6 is less than or equal, so that's why it's solid there. Okay, same reason why it was solid for the 2 because it could be also equal. Now all the numbers outside, those would be false because 10 is not less than or equal to 6. 1 is not greater than 2. 0, same thing. All right. Anything else in between these regions will be true. All right, so example 1, solve each compound inequality and graph its solutions. So in reality, what we really have here is we have two different inequality statements. We have 4 being less than or equal to x plus 2, and we also have x plus 2 is less than or equal to 8. So first things first, let's isolate the variable. We'll use the subtraction property. Notice how both of these properties happen at the same time on both sides. So at least the process is very familiar. These cancel out. So we have 4 minus 2, which is 2, and 2 is less than or equal to 2, or x is greater or equal to 2. You could notice symmetric property. You could just reword it this way, so just be aware of that. And whatever happened over here, we had these cancel out. It's less than 8 minus 2 is 6. So there we have it. There's our two solutions for this inequality. Now, how do we graph it? Because now that's the second thing we have to do, right? So x is greater than or equal to 2. So is that solid or dotted? Solid, right? Now, solid. Okay. Now it's greater than 2, so we're shading above. We're shading this way. Now, the question is, x is less than or equal to 6. Is that solid or dotted? Solid, right? Because it's equal to 6. And less than, meaning this way. So notice all this region right here is shaded in, and our 2 points right here are filled. Okay, so this is true, 4 is true, 6 is true, 5 is true, right? But everything else out here, those would all be false statements. All right, so let's look at example 2. Again, we have a compound inequality. That means 2 or more statements. In this situation, we have one statement saying -5 is less than or equal to 2x plus 3, and another statement, which is really just saying 2x plus 3 has to be less than 9. Now, how do we get rid of the plus 3? Okay, subtract, right? Because again, we're trying to isolate the variable. And again, notice, by the way, your process is very similar to the other statement, so be aware of that. All right, -5 with -3, right? That should be -8. Symbol stays the same. How to get rid of a multiplying 2? Divide, right? But what you do to one side, do the other. -8 divided by 2 is -4, right? 8 divided by 2, what's half of 8? 4, but it's negative, so -4. And 2x, how to get rid of, oh wait, we already got rid of a multiplying 2. Silly me bananas. All right. So let's do symmetric property. So in reality, x is greater than or equal to -4. That's one of our solutions. Let's look at the other guy here, the other statement. We have 2x is less than 6 because 9 minus 3, right? How to get rid of multiplying 2? Divide by 2, right? So x is less than, what's half of 6? 3. So notice you have these two statements. All right, so let's go here. We got -4. It's going to be solid or dotted. If you said solid, that means you understand what the equal symbol means. So go to -4, shade it in, okay? It's greater, okay, so it's going this way, and 3. So 3 is over here, but is it dotted or solid? Dotted, because it doesn't have the equal sign, right? It's just less than 3. So it's basically everything down below 3, but not at 3. So you could draw this. You could also shade it in. It's really up to you. Just remember, anything within this region between those two solutions will be true. Everything on the outside would be false. -4 is true because it's solid, but 3 itself is false, right? It's got to be less than 3, not exactly 3. And everything else above 3 is false too. But below 3, those are all true, for at least that statement. All right, so your term number 1, same thing, solve, all right, the compound inequality, and then 2, graph. Same thing with your term number 2, solve, and then graph. All right, so solving compound inequalities for involving the or statement or union. So we also call this a union, and you'll see that in geometry as well, which is a combined region with simple inequality graphs. So all real numbers less than 2. So that's what this is saying right here. All right, x is less than 2 or greater than 6. So less than 2, 1 is less than 2, 0 is less than 2, 2 is not less than 2, 2 is 2. Now is 3 greater than 2 or less than 2? No. Is 4 less than 2? No. Is 5 less than 2? No. Now 6, remember, or 6. So is 6 greater than 6? No. Is 7 greater than 6? Yeah. Is 8 greater than 6? Yeah. So as you can see, that's what's really happening here on this graph. Now, all real numbers less than or equal, all right, so that means boom, right away, there's a line underneath. That's what this means. So is 2 less than or equal? Well, it's equal. Is 1 less than? Yeah. Is 0? Yeah. Is 3 less than or equal to? No. 4? No. 5? No. Now, the other part of the statement is x is greater than or equal to 6. Now, is 6 greater or equal? Yeah, it's equal, right? Is 7 greater or equal? Well, it's greater. Greater or equal? Greater, greater or equal, right? So notice that's what's happening. All right, so example 3. Again, I'm going to solve and then graph. So let's go ahead and solve for our missing variable over here. That's 5. Okay, or how do you get rid of a -4 over here? Add 4 over here, right? So addition property. And 4 minus 3 is 1. So we have two statements here. So x is greater than 5, dotted or solid? Or hollow or solid? Hollow, right? X is less than 1, also hollow, right? Because it's not equals or equal, right? So x is 5. Where's 5? 5's right here. Again, hollow. 1 is right here. Again, hollow. Let's look at the statement. X is greater than 5. So any number greater than 5. That's this direction, right? 6 is definitely true. 5 is not greater than itself, right? So that's false. But let's look at the other statement. X is less than 1. Is 1 less than 1? No. So is 0, or negative 0, I guess, is 0 less than 1? Yeah. So we'll shade this direction because all these numbers this way are going to be true. All the numbers in between, like is 2 less than 1? No. Is 3 less than 1? No. Is 4 less than 1? No. So notice that's what's happening there. All right, so example 4, same concept. We got an OR statement. Let's solve for our single inequalities. How to get rid of a multiplying 2? Division, right? What you do to one side, do the other. What's half of 6? 3, right? So there's one of our solutions for our OR statement. Let's look at the other one. How to get rid of a multiplying 3? Divide, right? What you do to one side, do the other. What's, a third of 12? Or what's 12 divided by 3? Hopefully you got that. Now, x is less than or equal to 3. Is that going to be solid or dotted? Hopefully you said solid because it is also equal to, right? X is greater than 4 on the other hand, hollow. So numbers less than 3, definitely going this way. X is greater than 4, definitely going to bigger numbers, right? All right, so let's see. Where's 3? 3 is right here. It's solid, right? X is greater than, so here's 4. It's hollow. Definitely going this way, right? Because all the numbers that are bigger than 4 or larger than 4. And all the numbers that are less than or equal to 3. So that's how we would shade all this, because this would be true. 3 is less than or equal, right? It's equal. 2 is less than, 1 is less than, so forth, so forth. And again, that's kind of funny because negative 0, LOL. 4, that's false, right? 4 cannot be greater than 4. 4 is 4. 5 is definitely greater. 6 is definitely greater. So that's what's happening there. All right, your turn number 3. Again, solve, then graph. Same concept as before, just the last two. And then your turn number 4. Get some more practice. Makes permanent. All right, creating compound inequalities from graphs. So basically we have what? We have -1 here, we have 7 here. Let's see, they're definitely doing all the numbers that are less than -1 or equal to, right? So that's that. Or what do we have here? Numbers that are greater than 7 or equal to 7, right? Because it's true, right? True. And all the numbers going down, 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 down this way. And all the numbers from 7 going up and above. So that's what they're saying right here. So that's what you do. Basically the reverse of what graphing was. So again, same thing. We have 0. Can we be at 0? Yes. Can we be greater than 0? Yes. What about here? We got 6, right? So we could be less than 6, but not equal to 6, right? Because it's hollow. All right, so let's see. In terms of x, it's greater than or equal to 0, but it's got to be less than 6. So that would be how we bring these two together, because it's really an and statement. All right, so they're overlapping each other. All right, your turn number 5, same concept. What numbers are they dealing with? Is it dotted or solid? So is it going to be less than or equal, or just less than? Is it going to be greater than or equal? So try to figure that out. And then just like the last two examples, same thing, just different numbers, different practice. All right, so the real world, acceptable levels. So in the real world, we do this all the time. The reason you're alive is because we have the Goldilocks zone. It's not too hot, not too cold, right? So that's an inequality that we can express algebraically. So here we go, pH level. So this is talking about acidity in a pool. Uh, Basically, it's saying it's between 7.2 and 7.6 inclusively. That means it's including. So when you're thinking dotted or solid, that means it's solid. Now it's between these two points, right? So anything in between them is the true. So that's what we're looking at right here. Now it could be greater than 7.2. It could be exactly at 7.2, or it could be less than 7.6, or exactly 7.6, and that's what the graph shows below. So example 8, we got recommended chlorine level for a swimming pool. It's between 1 part and 3 parts per million inclusively. So I'm already thinking wherever my points are, they're definitely be solid. And it says between. So between these 2 points, it'll be true. So here's 1 part per million, including that, and 3 parts per million. And again, we're including that and anything in between, right? So anything in between would be true. Everything else outside our compound inequality would be a false statement for our pool. All right, your turn number 7. Alkalinity level is between 80 and 120 parts per million inclusively. Really important for fish, by the way. If you guys ever have fish, that's a serious, serious thing. They're super sensitive to all that. All right, so go ahead and graph it. All right, so there's your homework. I know it seems like a lot, but again, this is one of those meaty subjects that you really have to master. All right, so if you have any questions, feel free to come see me. And other than that, work hard, party hard.